Welcome PCS members and friends. Welcome to our today's PCS IBS seminar. It is a great pleasure to have with us Professor He Dahai. And I would like to invite our scientific host, Alexei, to introduce our speaker. Please, Alexei.
Okay, yeah, thank you, Tilan. So we have today Professor Dahai He from Xiamen University talking about from dynamics to statistical physics, chaotic route to thermalization. So Professor Dahai He received his PhD at the Hong Kong Baptist University in 2008. And then after a postdoc at the same university in 2010, he became an assistant and later associate professor at Xiamen University. And since last year, he's a full professor at the Department of Physics of Xiamen University. And as you can partially guess from the title of the talk, his interests are centered around thermal conductivity in lattice systems and applications, phonon transport in anharmonic systems, and relaxation and dynamical thermalization. And with this, please, Professor He, the screen is all yours.
Okay, thank you for a kind introduction, and also thank you for invitation to this interesting seminar. So today, let me minimize the screen. Okay, so minimizing the screen. So today what I'm going to present is about chaotic route to thermalization. So basically, let's do introduction in this way. If we look at the thermodynamic system from the microscopic level, so you will find that the macroscopic process is irreversible. But if you look at the system, the same system from the microscopic dynamics, and the dynamics are reversible. So in a long time, people try hard to make a bridge between the dynamics and the statistical physics. So today we're going to talk about about a method. I try to present a method to quantify a chaotic property called Lyapunov exponent. Then we can find a connection or a relation between the chaos and the thermalization. So basically, this is the main contents of the talk. So here's the outline. I will give a very brief introduction on chaos and the thermalization. Then I will introduce the geometrization of dynamics and the self-consistent phonon theory. Then we will use the method to calculate the Lyapunov exponent and Lyapunov time. Then we present some results. And finally, I will give a summary and discussion. So for chaos, there are many chaotic systems like double rod pendulum, Lorentz attractor, three-body problem. So the chaos means irregularity, random, and it's controlled by a determinist dynamics. So it's a very outstanding property is sensitive to initial conditions. So if we look at the two trajectory, very close at first, let's say the difference of the two trajectory at first is sigma 0. And after some time, you will find the difference is diverge in the exponential way. So you can see that sigma at time t is sigma 0 times e lambda t, and lambda is called the Lyapunov exponent defined here. And it gives a measure of the how the measure of chaos. Also, if you consider a many-body harmonic system, and you will get Lyapunov the spectrum of Lyapunov exponent. So normally we pay attention to the maximum Lyapunov exponent, because it gives an indicator of the onset of chaos. So let's take Logistic Map as an example. You can see that for two trajectories very close at first, and will diverge after a short time. It means it's very sensitive to initial conditions. And this map can be described by the bifurcation diagram, and it corresponds to the Lyapunov exponent as a function of mu. Mu is very key parameter of this map. So you will see that when mu is about 3.56995, about here, so you will see that the Lyapunov exponent becomes positive. So when it's positive, it means that the two trajectories will diverge, and means that the onset of chaos, which is correspond to the bifurcation map very well. So it means that the Lyapunov exponent gives the how fast it approaches to chaotic regime. So if we consider the inverse of Lyapunov exponent, it actually gives a time scale of the chaotic property. And the second concept is thermalization. In 1950s, Fermi and his colleagues conduct a numerical simulation on a very simple model, like which is drawn here. So they consider model which is it's like a harmonic potential, which is a harmonic interaction. If you consider it's a harmonic potential, so you will see that the energy of the mode or the phonon mode has no interaction with each other. So in this case, if we put energy in some mode, then the energy of this mode will persist, or generally they won't, the energy won't be changed. So the Fermi expect that if we add a very small nonlinearity to this system, and maybe because the vibration modes will interact with each other in this way, so the energy of the modes will become equilibrated, maybe, and this is their expectation. But however, it shows almost exactly periodic behavior instead of the expected ergodic behavior. So this is the result of their numerical simulation, and they put the energy on the first phonon mode. Then with the increase of time, other modes like the second, third, the fifth mode are excited. But as time increases, you will find that almost all the energy come back to the first mode, and the other modes almost has balancing energy. So this is very strange. It seems that equipartition cannot be reached, and similar phenomenon has been observed in optical systems. But in 1980s, and people argue that the Fermi-Pasta-Ulam recurrence results from the presence of metastable state, and which owes to KAM Tori, and may persist for extremely long time. But after a long time, the equipartition will eventually reached. So this is numerical verified by the two studies here. And this, for the first study, is conducted by Professor Fra and his collaborators. So after that, people realized that the equipartition, the the system has the capability of the equipartition, no problem. But the immediate question is how fast a system can be thermalized. That means how fast a system approach to equilibrium state. And there are many studies for a long time. So a recent study, actually several recent studies done by my colleagues at Xiamen University, they find that the thermalization time is proportional to a parameter called non-integrability strength, eta. I will come back to this parameter later. So it means that there's a scaling behavior with respect to the non-integrability strength. Actually, this parameter is given by the U. U is the linearity times energy density epsilon, n minus 2 divided by 2. So n is I will describe what is n data. So similar observation is found in quantum system. You can see the 2, the power 2 also in quantum systems. So so this is an interesting result, and because linearity plays a main role for the thermalization, so people may ask, what's the relation between chaos and the thermalization? So in 1990s, Patini and his collaborators, they conduct numerical studies on Lyapunov exponent, maximum Lyapunov exponent, and also relaxation time defined in their paper. And they find that the Lyapunov exponent undergoes a transition when the energy density of the system increase. And there's a transition point of the energy density here. So that means that by scaling behavior of the Lyapunov exponent, but they find that this scaling law is epsilon to 2/3 and minus 2/3, and this positive 2/3, and we will see that, and this is long. And for the relaxation time described by the open circle, and they use this name, Kolmogorov-Sinai-like law. Actually, it's a stretched exponential formula to fit their numerical result. And they argue that after the transition point, the relaxation time becomes a constant. So this is strange, and we will see later that the constant in the large energy density regime is long. So another study is conducted by Professor Fla's group. This is they give a very interesting definition of aggregation time, very smart definition, and what they observe is that the aggregation time behave qualitatively different with the Lyapunov time, and for me this is a little bit strange because when Lyapunov exponent is large, that means Lyapunov time is short. The aggregation time should be large accordingly. But this one gives a very contrary result. And also in last year, Professor Abhishek Dar's group, they give numerical studies, and they find that the thermalization time defined in real space, in real they don't do study in the mode space, K space. The thermalization is conducted in real space. And they find that the thermalization time is positively correlated with Lyapunov time. But their result shows that the scaling law depends on a parameter gamma. The gamma is a parameter with respect to initial condition. And this is also seems strange because it's initial condition dependent, the result. So also for Lyapunov exponent, people also observed scaling behavior in various models, like alpha beta model and beta model. And for beta model, which is given by this green line, and the exponent is what they observe is 1.9. So in our study, we are sure that in an explicit way, actually the scaling law is the scaling exponent is 2. So let's do let's in short. Now we have the knowledge for the thermalization time in quasi-integrable regime, which is proportional to eta minus 2. But for Lyapunov exponent in a quasi-integrable regime, and the scaling exponent is not clearly determined. And not to mention that the regime beyond quasi-integrable, and we have no knowledge about this blank. And also we don't know the case for thermalization time. But if we know all these blanks, a further question can be asked: what's the quantitative relation between chaos and the thermalization? The difficulty lies in we don't have a powerful analytical approach to Lyapunov exponent for generally harmonic system. In this way, we can one can determine the power in explicitly exactly. So,
Professor, excuse me, we have a question
yes.
from Dominic. Dominic, please.
Okay, thanks.
Okay.
Yeah, maybe you said this, but I must have missed it. So how do you, this is a quantum system that you want to study, but then I
this
wonder
is a
how
classical system, sorry.
So the Lyapunov exponents are properly defined, because in quantum systems, I wonder that they are not, there is not really a definition of those, right?
Yes.
Right,
And
but you don't need to worry because
exponent is uniquely defined.
But you don't need to worry because you study just classical systems.
Sorry?
You don't need to worry because you study just classical systems, right?
Yes.
So for you, everything is defined. Okay.
Yes.
All right. Okay, thanks.
Okay, thanks. So we will propose a approach based on the dynamical geometrization and the self-consistent phonon theory to quantify the Lyapunov exponent explicitly. Then we will answer all these questions. So here I will introduce the geometrization of dynamics. Note the two facts. For Hamiltonian dynamics, the trajectory of Hamiltonian system is the achievement of the Sn function. And here L is the Lagrangian function of the system. And if we look at the same system from the geometric way, the geodesics of the Riemannian manifold are the achievement of length function defined here. Here, Gij is the metric. So by means of a suitable choice of the metric, then the dynamical problems can be transformed into problems on geometric manifold. We will see it later. So generally, we have two two metrics are commonly used. One is a Jacobi metric, and the other one is Eisenhardt metric. It has been proved that the geodesics correspond to the trajectories of the system. And in our study, we use Eisenhardt metric. And the advantage of using the geometrization of dynamics is that we can transform the original stability analysis of the dynamics to stability analysis of the geodesics of manifold. So it means that if we know the stability of the geodesics, then we know the stability of the trajectory, and we know the chaos. So,
Professor He, we have another question. Dario has a question. Dario, please.
Yeah, sorry, maybe I'm missing one point. I mean, here you are saying for a choice of the metric, but as far as I see, the metric is not your choice. I mean, the metric is dictated by the dynamical system that you are considering, right? I mean, let's say the potential determines what is the metric.
Yeah, yes. Because
okay.
we have a different way to choose metric, but
I see. For a fixed potential, you can choose the metric in different ways.
Yes.
And both of them are well-defined metrics, let's say. I mean, they satisfy all the properties that a metric should satisfy.
Yes.
Okay.
I would like to say that this guy, we are simplifying our calculation, and this guy may be more complicated.
Okay, but let's say the lesson and the results that you get are just quantitatively affected by this choice, but qualitatively not? Or, I mean, how much this freedom affect the results?
I haven't conducted this guy calculation, but I think they will give the same solution because this is the same system.
Okay, thanks.
Okay.
Sorry, we have another question from Dominic.
Yeah. Please.
Yeah, so, I mean, to answer maybe Dario, I think it's just you choose any coordinates because they are general coordinates. You choose the coordinates that will lead to Hamiltonian equations that are simple to solve. That's all there is to it, right?
Okay, but so can you show that different metrics correspond to, let's say, canonical transformations of the coordinate? Or I mean, can you relate the various metrics in some way such that you see that the results are unaffected or not?
Because I don't have conducted this calculation, I don't have some conclusion.
Okay.
If I may, I think those are called Legendre transformations, no?
Yes, because actually the theory of the geometrization has been developed a long time ago, and you can find it in textbook.
Okay.
Yeah.
Okay. Thanks.
Okay, so here's the main very brief idea. You add the perturbation to a geodesic Q, and let's consider I component. So you add a perturbation Ji to the geodesic line, and the perturbation follows the Jacobi equation given here, and here I is the Riemann curvature. So from this equation, one can see that the instability of the geodesics is completely determined by the curvature of the manifold. But this is very complicated equation, and we have to make some assumptions to simplify the calculation. The two main assumptions given here. One, we assume the manifold is quasi-entropy. That means the tensor equation can be simplified by a scalar equation by Ks. And another one is that if you consider a very high dimensional harmonic system, and one can assume the dynamics of geodesics is chaotic. So in this way, then one can obtain the effective Jacobi equation, which is stochastic differential equation given here. And here K is the effective Riemann curvature. And one can assume the status of the effective Riemann curvature is the same as that of the rigid curvature Kr, which is the one we want to calculate. And the rigid curvature based on the Eisenhardt metric is defined here, the Laplacian of the potential energy. Then the average rigid curvature per degrees of freedom can be defined by here. And here the average Kr, the average is with respect to microcanonical average. And this guy is the fluctuation of rigid curvature. And the two guys are important for our following calculation. So according to the Van Kampen's theory on stochastic differential equation, and the maximum Lyapunov exponent is given, lambda is given here. Here you can see that both large lambda and the tau, big lambda and tau, is a function of the K0 and sigma k. K0 is the average rigid curvature, and sigma k and is fluctuation. So once we have the two guys, then we can obtain the maximum Lyapunov exponent, and Lyapunov time is defined as the inverse of the maximum Lyapunov exponent. So let's look at by this cartoon. So the advantage of this geometrization of dynamics is that one can see the origin of chaos. You can see that if look at a manifold which has a positive curvature, then if you look at geodesics and another one is perturbative, you will see that the two geodesics will follow with each other. That means they don't diverge. The difference don't diverge. But if curvature is negative, the manifold is always look like a saddle. The saddle-safe manifold will lead to the two geodesics diverge in an exponential way. So even for a complicated system, which is not always, which has not, whose curvature is not always negative, but if you increase the energy density, and the manifold becomes fluctuated. So if you look at some local places like here, you will see the similar saddle-shaped manifold. So at least local places, the geodesics will diverge in an exponential way. So that's basically the origin of chaos from a geometrical perspective. But more than that, this theory can quantify chaos by calculating the maximum Lyapunov exponent. But generally speaking, because we have to know K0 and sigma k, the average rigid curvature and the fluctuation of rigid curvature. And generally, the average of the two guys is not easy to calculate. One have to use the numerical technique. So the question
Professor
is,
He,
yes.
Sorry, we have a question from Dominic.
Okay, please.
Hey, it's me again. So I'm looking at this Ricci curvature, and I wonder, because you draw this sphere and the saddle, but I wonder what kind of space is this at? Is it like physical space, like three-dimensional physical space, or is it, let's say, phase space, which means like three?
This is only some cartoon because the Hamiltonian system is very high dimensional. We only choose just some.
But the manifold is defined on phase space. Or which space is the, like these pictures, do they correspond to the phase space or configuration space?
Let's say this is correspond to phase space.
Okay. So it's okay. So it's really like 2n to the power of 3 dimensions. No. Yeah. Okay. So it's big. Thank you.
Okay. Okay. So now the problem is how to calculate the average ridge curvature needs fluctuation in an analytical way. By that we can obtain the maximum Lyapunov exponent explicitly. So we will use the second technique called self-consistent phonon theory. So the main idea of this theory is that let's consider a Hamiltonian which represent the system given here and interacting oscillators. So here W is the interaction potential and V is the onset potential. And the equipartition function is given by this way. So this is a normal procedure, but this guy is very difficult to calculate. Normally we cannot do it. And the main idea of the self-consistent phonon theory is to use a tri-Hamiltonian to conduct a canonical average. The tri-Hamiltonian normally is given by a quadratic way. Here, this guy is the quadratic interaction potential, effective interaction potential, and this guy is the effective onset potential, and with two parameters, Fc and the F to be determined in a self-consistent way. So how to determine the Fc and the F? So let's look at the Feynman-Jensen inequality. It gives the upper bound of the free energy of the original system, F. And this guy, the upper bound consists of the F known, which is the free energy of the tri-Hamiltonian. And this guy is the canonical average of the difference of the Hamiltonian, original Hamiltonian, and the tri-Hamiltonian. And this average is given with respect to the tripartition function. And by minimizing the right-hand side of the Feynman-Jensen inequality, then one can obtain a normalized phonon frequency given here. Here, V law and W gamma is the average of the onset potential and the interaction potential given here. And the law square, the parameter law square and gamma square are written in this way. So if we put law square, gamma square, and omega p square together and solve it in a self-consistent way, then we can determine F and the Fc. And once the F and the Fc is obtained, then we can do the canonical ensemble average. But the problem is that what we want to calculate is the average ridge curvature with respect to microcanonical ensemble average, because what we consider is an isolated Hamiltonian system. So then we have to make a transformation from the canonical ensemble average to microcanonical ensemble average. For a quantity, physical quantity A, the average microcanonical average given here is equal to canonical average once the mean energy of the canonical system is equal to the energy of the isolated system. But the problem is that for the canonical average, you have to use a quantity named temperature. So, but for isolated system, there's no such a quantity, temperature. So we have to make a link between the temperature and the energy density, which is given in this study. So for fluctuation, it's a little bit complicated. One have to use Lebowitz-Purkis-Verlet formula given here. Here CV is the heat capacity. So once we can do this calculation, then we can get the average ridge curvature and its fluctuation in a microcanonical way. So the maximum Lyapunov is important. So everything is ready by now. So let's take a model, say FPUT-like model as an example. So the model is like the FPUT model, original FPUT model, but with exponent n in the interaction potential. When n equal to 4, the model reduced to original FPUT model. So for the sake of simplicity, in this study, we only consider even n. And for this model, the non-integrability strength can be defined by this guy. Here, U is the nonlinearity strength, and the epsilon is energy density of this system, and n is the exponent n here. Okay, so in terms of self-consistent phonon theory, the effective harmonic constant F is given by this equation. Then the energy density epsilon with respect to temperature T is given by this guy. So the ridge curvature for the FPUT-like model based on the definition is given here. So the average ridge curvature with in the sense of canonical ensemble average is given by this equation. And the fluctuation also of ridge curvature also can be given here. And now the remaining task is transform the canonical ensemble average to microcanonical average. So finally, the average ridge curvature with in the sense of microcanonical ensemble average is given here, and its fluctuation is given here based on the Lebowitz-Purkis-Verlet formula. And finally, when these two guys are ready, the maximum Lyapunov exponent is available. So now everything in this equation is can be explicitly obtained. So then we can get the formula for lambda in an explicit way. So let's take two limits. One is the quasi-integrable limit. So in this limit, the non-integrability strength is very, very small. And in this regime, let's look at the equations here. Then you can find that the average ridge curvature actually is a constant 2, about to equal to constant 2. And its fluctuation is proportional to eta square. So in this sense, the approved time obeys scaling behavior, eta proportional to -2. So know that in previous study, people find that the thermalization time is also obeys the same scaling behavior. So that means the two time scale actually are the same in some sense. They have a difference, constant alpha. Here alpha is the nonlinearity and the energy density independent. So this equation gives a proportional relation between the thermalization time and the Lyapunov time. And it's quite simple. So let's verify the theory here. Here we use we conduct some numerical simulation to calculate the average ridge curvature and its fluctuation along a long-time simulation dynamics. Then, based on standard procedure, one can obtain the maximum Lyapunov exponent based on the definition here. And for our integration, we used a symplectic algorithm of 10-order symplectic integrator. And this is a very precise algorithm which guarantee the fluctuation of the dynamics is very, very small after a long-time simulation. So let's look at the result. So for ridge curvature, this is the left plot gives the average ridge curvature as a function of the non-integrability strength eta. So we can see that the theoretical result agree with the simulation result very well for both n equal to 4 and n equal to 6. And for its fluctuation of the ridge curvature, and also we find a very nice agreement between theory and the simulation. It gives sigma k square proportional to eta square. So we can see that the Lyapunov time also agree with the simulation results. So, and it gives the such scaling behavior for by simulation and the theory. So that's in some sense it verifies this relation. And interesting is that in another limit, strong non-integrability regime, that's a strong non-perturbative regime. And we can also find scaling behavior when eta is larger than 1. So for average ridge curvature in this regime is proportional to eta to 1 over n. And its fluctuation is proportional eta 4 over n. So Lyapunov time obeys the scaling law eta minus 1 over n. So it's very interesting in this region. We also have a scaling behavior for Lyapunov time. But what we don't know is the thermalization time. We will look at it later. So let's verify our theory. So we can see that again, the simulation agree with the theory very well in a very large range of the eta, from 10 to minus 4 to 10 to 4. This is a very surprising result for me at first. So, so we can see that there's a biscaling transition for Lyapunov time. And actually one can determine the transition point here in this way. So we can do this calculate transition point by this way. Let's look at the intersection of the two scaling lines, and the intersection define the transition point eta tr. So in terms of self-consistent phonon theory, the transition point can be determined in explicitly. So we can see that this is the dashed line indicate the transition point. We can see that it gives a very nice indication of the biscaling transition. So
Professor He,
yes.
We have one more question from Dominic.
Please go ahead.
Yeah. So I wonder about this graph. So could you explain physically what is this x-axis? So I assume on y-axis there is this Lyapunov time, but what does it mean? What am I looking at?
You mean the so maybe we can understand it in this way. So the Lyapunov time is the inverse of the Lyapunov exponent, which give a measure of the chaos, the strength of chaos. So when time is very large, that means Lyapunov time, the Lyapunov exponent is small. So in this way, so in this regime, we have diffusion plus the resonance of the modes. So the route to chaos is very fast. But in this regime, we only have a very diffusion. Sometimes it's called annual diffusion. It's very slow. It's very small. The way the route to chaos is very, very slow. So
and then the transition, what does it? Can I see the transition somewhere, like physically? What physical point does it correspond to?
I think the transition separate, give a separation of the two, give separation of when the resonance will occur, or when the resonance plays the lower.
That the resonance becomes smaller, or there's I'm not sure if I'm getting it.
I think the first question by Dominic is what is the meaning of eta? So maybe you can reiterate and tell what eta.
Yeah, if you freeze the energy density, you can regard eta as the nonlinearity strength U.
So when eta becomes small, you have a very weak nonlinearity.
Yes.
Right, and then can you show please again the Lyapunov time figure which you had before?
Here.
So then I was a bit puzzled because you pointed to the right part of this figure where eta is large and said this is where you enter the Arnold diffusion regime, but this is strange, right? This should happen actually for small eta. I mean, large eta means.
Yeah. Sorry, this is a time scale, not exponent. Right. Yeah. This is times. Yeah, you are right. I mean, this is the Lyapunov time is the inverse of Lyapunov exponent.
Sure.
Yeah. When Lyapunov time is small, it means Lyapunov exponent is large.
Yeah. So your almost integrable dynamics or whatever, or weakly non-integrable dynamics happens in the left part of these plots. So for small values of eta.
And the right part is the chaotic one.
I would say they are all chaotic. It's just weak versus strong or something like this.
Yes.
I have a question actually. So what are the initial, so for the simulations, what kind of initial conditions do you use?
When you say what's the initial condition?
Well, okay. By simulation, you mean that you simulate some what is this? An FPU system, right?
Right.
Right. So each value of eta, okay, corresponds to some effective nonlinearity. What about what's the energy density in the system?
Yes. We can actually. I have more results. We can do the simulation in the two ways. One is freeze nonlinearity and increase the energy density. Another one is freeze energy density and change linearity.
Good.
So
whatever you do, maybe what my question is, if you do a simulation, what kind of how do you choose your initial condition of your trajectory you can integrate?
Can I reply later to you by email, because the simulation is conducted by my student.
Sure, we can discuss this later. Sure. Thank you.
Yes. I will reply how we choose the initial condition of the simulation.
But still, I mean, it's a bit important to understand this at this stage here, because you say that you have you observe this kind of crossover from strong to weak chaos, and then of course the question is, well, is this a generic phenomenon which doesn't depend on the particular choice of your initial condition?
Yes, I can. Yes, I can reply this. Yes, we don't. The result is initial condition independent, and this is different with Professor Dah's study.
Thank you.
Okay. Let's continue. So now the remaining question is the thermalization time. So we can calculate it based on the standard procedure, do some canonical transformation. Then you can define the energy of the phonon mode. In this way, then you can define the indicator of thermalization. Then you finally can calculate the thermalization time by let the indicator equal to some constant. So, but problem is that if you want to look at the thermalization in non-perturbative regime, and one cannot use the bare phonon frequency like what they do in the quasi-integrable regime. So in this non-perturbative regime, the phonon frequency should be replaced by a renormalized phonon frequency, which can be obtained by the self-consistent phonon theory. Then the energy of the phonon mode is given by this way. So here, omega k square is the renormalized phonon frequency. So only in this way, and we can get well-defined thermalization time in the non-perturbative region. So this is the main result. We give the comparison between thermalization time and the Lyapunov time. Sorry. Then one can see that the two time scale consistent with each other in a very large range of eta. From eta.
Can I ask a question?
Yes.
I missed that point. So yeah, actually I didn't understand what is thermal. How do you define thermalization time again? Can you?
Yeah. Let's see. Let's look at the slide. So this is a standard definition. We define the indicator of thermalization, which zeta. This guy is given by the by this equation. So you can see that the summation of this one is from n/2 to n, and this one
this is again for an arbitrary initial condition, or do you excite here only one, let's say, a mode?
Arbitrary.
So you excite, I could, for instance, choose all modes to be excited to the same energy.
What we do is two simulation tests. One is we excite only one mode. Let's remember. Let's recall. Let me recall. And another one is we only excite some modes with small k, maybe the k equal to 1, 2, 3, 4, 6, 8 to 8. Only excite 8 modes. So, but they give the same results.
No, wait. So again, so you now you say that your initial condition is one where you excite only a limited number of low frequency modes.
Right.
Right. Well, then this is not a random initial condition on the energy hypersurface. There is a constraint here. And I'm wondering whether your thermalization time, which you obtain from that, has anything to do with, well, thermalization times, which I could try to define for some generic trajectory on my energy hypersurface. Because why I'm saying that is because we have tried to do that by starting from random initial, some arbitrary initial condition, and then measuring some properties of finite time averages of observables. And what we found is that the thermalization time seems to be, let's say, seems to scale as the square of the Lyapunov time.
Okay.
Means, of course, that there's another time unit involved in order to get the units straight again. But still, this was the outcome of our study for these Fermi-Pasta-Ulam-like systems for weak nonlinearities, no? For this.
Okay,
so
Professor.
I'm a bit puzzled here. How you?
Professor Frau, maybe I will check with my student and reply this initial condition problem to you later.
Okay, thank you.
I think yeah, this is an important question.
Thank you.
Yes. Okay. So by this definition of the energy of phonon modes in the non-perturbative regime, then we can obtain thermalization time. Then one can see the agreement between the time scale, two time scales, for both n equal to 4 and n equal to 6, but with different alpha. For for this plot, we have used the alpha is a fitting parameters, but and is only one quantity is for all the range. So we can see that the proportional relation is established even beyond the quasi-integrable regime. So it means that there's a very close relation between the chaos and the thermalization. So in this sense, then we can, if this relation is valid, then we can say the thermalization time in this non-integrable regime is proportional to eta minus 1/4 for n equal to 4, and proportional to eta minus 1/6 for n equal to 6. So that's the main idea to get the scaling behavior of thermalization time. Because so far we don't have a powerful technique to calculate some analytically calculation of the thermalization time in the non-perturbative regime. But based on the proportional relation, then we can get the scaling behavior for the thermalization time in this regime. And know that this is consistent with the mode coupling theory conducted by Lepre long time ago. They defined realization time in terms of autocorrelation function. And in terms of mode coupling theory, they find that realization time is proportional to energy density epsilon to minus 1/4, which is consistent with the formula defined here, given here. So finally, I will give because because I have the time run out, so I will give a very brief understanding of the relationship with coarse-grained entropy. So what's the thermalization? Thermalization process is a process of loss of memory of the initial condition. And this means the entropy production of the system. But according to Liouville theorem, the phase volume is conserved. That means the conservation of the fine entropy defined here. So, but since the thermalization process is irreversible, so the process of entropy increase actually comes from the increase of coarse-grained entropy. And the mean rate of the coarse-grained entropy production is the famous Kolmogorov-Sinai entropy. So if we look at the coarse-grained entropy, so you can see there's an additional term here, and the C square n is actually the number of coarse-grained states. Here, n is the density of state along the surface of, and C is the coarse-grained size. So result of coarse-graining is to include all the surrounding C square n represented points or represented states into the calculation. So for Hamiltonian system, the mean rate of the coarse-grained states, coarse-grained entropy is proportional to maximum Lyapunov exponent, and that means the chaos entropy is proportional to maximum Lyapunov exponent. So because this guy indicates the information loss, and this guy indicated how fast the system approached to chaos. So in this way, the average rate of the information loss, the two time scale can be determined in this formula. So this is a rough understanding, not the rigorous derivation. So in summary, we developed an analytical approach to Lyapunov exponent for general Hamiltonian system based on dynamical geometrization and self-consistent phonon theory. And to answer all the problems proposed before, we now know that for Lyapunov time is proportional to eta minus square in quasi-integral regime, and beyond quasi-integral regime is proportional to eta minus 1 over n. So if we also find the quantitative relation between chaos and thermalization represented by this relation, and if the relation is valid, then we can find the scaling behavior of the thermalization time. So basically, this is the main results of this study. And we can have two discussions. So one is that this relationship now is verified in a FUT-like model, but it should be verified in more Hamiltonian system. And the second is one, we can see in the previous studies that there are many ways to define a time scale for the thermalization process or relaxation process. And the thermalization time defined in our study is proportional to an intrinsic time scale. It's named Lyapunov time of the system. So this might indicate that the one defined is well defined as for describing the thermalization process. Okay, that's all I want to present. So I would like to thank you for your listening. Thank you.
Thank you, Professor He, for your excellent talk.
Thank you.
And we have time for questions. So perhaps let me start. So you've mentioned that you've tested for these FPUT-like models for n even. So what about, you said n odd is more problematic. Can you maybe just comment?
Yeah, this is a good question. Actually, the referee also asked us, and I would like to say in this way, in principle, we can do the similar calculation by the same procedure, but it will be very complicated, and maybe we cannot get such a beautiful explicit formula.
Mm-hmm. It has to do because of the somehow evenness of the. In even case, it's maybe easier to do integrals, or what they simplify.
Yeah, you are exactly.
Mm-hmm.
I can say something more than that. For self-consistent phonon theory, if the interaction, the n is odd, it means that the interaction potential is asymmetric. So here you will have an additional parameter to be determined, which correspond to the thermal expansion. But we have done that in many years ago for FPU alpha beta model. But what we don't know is for generally odd n case, we don't do this kind of calculation. But for alpha beta model, it can be done.
Mm-hmm. Okay, thank you.
For another, additionally, for if the model n is odd, for example, n equal to 3, and the system is unstable, you mean you will diverge. But if we consider FU alpha beta model, then there's no problem. But for FU alpha model, for n equal to 3, and you have to consider a very small nonlinearity case.
Mm-hmm. Okay, thank you.
Thank you.
Do we have any? Dominic has a question.
Yeah, I wonder with this Kolmogorov-Sinai entropy, if you go to that slide, what kind of definition do you use for this Kolmogorov-Sinai entropy? Because I think there's like some kind of definition of finer and finer coarse-grainings in the limit. But
yes, the definition is given here. Now the problem is how to define the coarse-grained entropy, and in our sense, we use the definition here. So this is based on Boltzmann entropy.
Mm-hmm.
So and this guy, so let me minimize it. And this guy.
So what is Cn?
So
C squared and what is n?
So if you can look at the system in a very precise way, you need a coarse-grained. Then here you have only one represented point. But because you cannot do it in such a precise way, so you have to include all the surrounding points into your calculation. So n is the density of states along the surface, and C is the coarse-grained constant, the size, coarse-grained size. So C square is kind of surface area and times.
So this picture is a picture of phase space, or is it a picture of just position?
This is picture of phase space.
Oh, I see. So these dots are the really phase space points.
Yeah, actually this is the evolution of the phase space. This is cartoon to represent the evolution. You can see.
Right. So the C is just some parameter that you choose to be small, but it's fixed in this definition.
Right.
I see. Yeah, I've seen the different definitions of Kolmogorov-Sinai entropy, but they all look very different, so it's not clear to me that they are the same. But I think there's a theorem that states that you can write it as the sum of the positive Lyapunov exponents, which is why now I wonder about this. As you show, for a Hamiltonian system is proportional. Because certainly should be equal to sum of all the Lyapunov exponents. Well, all the possible.
Yeah, generally speaking, the chaos entropy should be a function of all the positive Lyapunov exponents.
Right.
But yeah, but for I mean, I don't have a rigorous derivation, but for general Hamiltonian system, for a Hamiltonian system, or for some Hamiltonian system like FUT-like model, and you can see the Lyapunov spectrum actually is linear. It means that you can use the maximum Lyapunov exponent to represent all the other positive Lyapunov exponents. So to some extent, the positive relation here is correct.
Oh, I see. Yeah, I was thinking in terms of my research, like, because
minus
I work mostly
sorry,
in terms of my research that I do. I work with quantum coarse-grained entropy. So I was wondering if one could use this coarse-grained entropy, the quantum version of it, to define Lyapunov exponents for quantum systems. Because it seems that
I think Professor Flower is an expert. I have no idea.
Okay, no problem.
For quantum system, actually, for me the quantum chaos is very complicated. Yeah, I have no idea about quantum chaos.
All right, thanks.
Okay, do we have any further questions from the audience?
Let me maybe add some. So on this Kolmogorov KS entropy discussion, I don't. I'm not sure what was meant, what you meant by this linear dependence. But I mean, sure. I mean, let's say we have a whole spectrum. So the KS entropy is the sum of all the positive Lyapunov exponents. Right. So let's say there is some functional dependence of lambda on its on the number, so to say, of the exponent. Fine. But the proportionality which is written down here implies that if I change the largest Lyapunov exponent by, let's say, a factor of 2, then the KS entropy will also change by a factor of 2, which assumes actually that this linear dependence which you quoted before is, so to say, staying intact. That there is a very so that has a very strong implication on some kind of scaling property of the entire spectrum upon the change of some parameter, which will, let's say, lead to a change of the largest Lyapunov exponent by whatever, a factor of 2 or so. Mm-hmm. And that's quite a strong statement, I would say, which yes. I'm not so sure whether that's actually true all the time. Mm-hmm. If we interpret this proportionality,
yes, actually, maybe I can use a slide to reply. Actually, according to Paschen's theorem, the chaos entropy is a summation of positive Lyapunov exponents. Mm-hmm. But in some previous studies, it shows that for some condition, the chaos entropy is proportional to the maximum Lyapunov exponent, since the Lyapunov spectrum is almost linear. So if it is linear, so the summation of the of lambda I, it will be proportional to lambda measurement.
Well, yeah, sure, if it is linear. So I think there are cases, it's easy to come up with cases where it's not. And then, okay, yeah, sure. So if you, of course, if you assume that it's linear, then sure.
Yes.
But what I'm trying to say is that it's actually not at all, must not be linear. And as far as I can tell, it's not in a number of cases one can study. I see.
Yeah, I know this relation is quite strong, but yeah, if it's
I see.
Go back to this relation. So if the thermalization time is positively related to Lyapunov time, and it is understood, but now it's linear proportional to this guy. So this is, I think there may be some deep features under it.
Well, I think this is something I'd actually, as I discussed before, as I mentioned before, this is something I don't really understand, because well, I do understand that in the way you defined the equipartition or thermalization time, but what I'm trying to say is that it's not at all clear whether that is so. As you mentioned, also we can define many different thermalization or whatever times, and then the big question becomes which one is the preferred one. Moreover, also things depend on the choice of initial conditions for trajectories on which we want to compute some thermalization time. And I think the one which you quoted here seems to be depending on the initial conditions. So because initial conditions are chosen such that only low frequency modes are excited initially, which is not a generic random initial condition situation. Of course, if you choose an initial random a random initial condition, then the way the thermalization time calculation is defined becomes not very meaningful, which maybe means that this is an example of a time which is initial condition specific, and which brings me back again to things we did in the past, where we have defined, for instance, times just by measuring the relaxation of the mode energies, which become exactly conserved quantities in the very zero nonlinearity integrable limit. And if the nonlinearity is non-zero, then you find some finite relaxation times of these energies, and these times were measured for random initial conditions, and the scaling was different. So we didn't see this linear.
Yeah, may I make sure that so you just mentioned that for if you apply the random initial condition for some system, then you get a finite relaxation time, even the nonlinearity is equal to 0.
No, I didn't say that. I said that we used another definition of thermalization time by measuring the time dependence of the mode energies. Yes, but in a different way, such that the measured times become independent of the choice of the initial conditions. So we chose random initial conditions. All we made sure is that we sit on the energy hypersurface. And what I'm saying is that if we measure times that way, we come to a different conclusion, namely that these times do not scale linearly with the Lyapunov time, but differently. Why and how is a different story, but not linear.
Yeah.
That's why I hooked up on your linear relationship and asked, how do you define your thermalization times?
Right. I will check with the how we use the initial condition, and I will give you a reply. Yeah, this is a very good question.
Mm-hmm. Thank you.
I think Dominic has more questions or comments.
Yes, please go ahead.
Oh, no, I just forgot to put my hand down. I'm good.
Ah, okay. Then I believe Alexei also wanted to ask something.
Yes, my question though is very simple and generic. I'm actually curious, so the geometrization approach, so you used it for Hamiltonian systems. So what about, does it still work for discrete, like for maps? Can you still use it?
Right. I'm not so sure, but for geometrization dynamics approach, maybe you can apply to discrete system, but I'm not so sure. But I'm quite sure is for the self-consistent phonon theory, which is given here, and sorry, it's given here, and I think it's not applicable to discrete system.
Okay.
Okay, do we have any other questions from the audience? In case not, let us thank Professor He again.
Okay, thank you all.